So let me start by showing you a photo. Who of you knows what this is? Most of you, right? So this is the horse in motion captured by Edward Muybridge in 1878. So it was just in the early days of Stanford, maybe just before it was founded even. And he was commissioned by Leland Stanford to prove that the horse has all 4 feet up in the air in a particular trot, right? And we can see that in these photos up there. So that's a form of high-speed photography. It wasn't known, or people couldn't prove that it was actually possible at the time. So what Muybridge had to do is he actually had to design a photographic, an experimental photographic setup where he has actually an array of cameras, a lot of different cameras in a line. There are all these lines spanned across the track, and the horse would trigger each of these cameras. There would be a mechanical shutter falling down and expose the horse to capture all these different sequential parts. So Muybridge really had to develop new imaging technology to see something that people hadn't seen before. And in my understanding, that's a form of, experimental imaging. That was the first camera array at Stanford. Mark Levoy and his group actually built a digital camera array here, maybe about 10 years ago now. But if you want, imaging is the oldest discipline at Stanford, in my understanding. So what do we do today? Where has imaging gone? So today, what our group is focusing on, for example, is computational imaging. So that is the co-design of optics, electronics, and modern signal processing optimization. So most of the time when we think about photography and displays, we think about geometric optics, so that's ray optics. We think about light as rays, but we actually work a lot on wave optics too. We have optimization, signal processing on the other hand. But I would say if I could describe computational imaging, it's really this bridge in between these 2 different fields. And computational imaging, this co-design of optics, sensing, and computation, has been delivering a lot to us, and you may not be aware of it. So some of the early work in this field was high dynamic range imaging. So the idea being that any image you can take of a scene will be limited in contrast. So in order to capture a scene that has an extremely high contrast, you want to capture multiple different photos with different exposures and then digitally fuse them together. That's a feature that you probably have on your phone today. It's called HDR imaging mode. You can capture extremely bright objects next to extremely dark objects. And that's something that came out of our community. Super resolution, extended depth of field. So the idea of collecting a lot of light with large apertures while maintaining the focus throughout the entire image. Light fields, something that was pioneered at Stanford here and is now going into the consumer electronics industry quite a lot with companies like Lytro that came out of Stanford also. And the idea of compressive imaging really necessitates computational reconstruction on the kind of data that you capture. So all of these are just a few examples of where computational imaging has already made an impact. If you think about HoloLens or any of these head-mounted displays that have sensor arrays on them, I mean, imaging is there. Image processing, computer vision, computational imaging is ubiquitous. So in our research over the last 5 years or so, we've demonstrated that this idea of co-designing optics and computation also makes sense for displays. And in this case, you normally design user experiences. So you co-design optics, electronics, but to create different types of experiences. So you need to also have a pretty good understanding of the human visual system in order to design these experiences. And examples of this include the high dynamic range display that was invented around 2004. That's now in every single television. If you go to Best Buy, you basically have control over the LEDs that re-illuminate your LCD, and that just increases the contrast that you can generate compared to if you just use a standard backlight, which is what most people have been doing before. Super resolution displays is something that's most projectors. I bet this projector right now has some type of a super resolution integrated in it. Texas Instruments, the DMDs, all have some type of super resolution. That's something we've been doing a lot of research on as well. Light field displays, and that's something I'll talk about more in this talk, is something that's emerging. So you can think about a light field display as a television that gives you a 3D effect without you having to wear glasses. Most people don't care about stereoscopic television so much, but in this emerging space of wearable electronics, virtual reality, augmented reality, we can use the same technology to create focus cues. And I'll show you in a second what that means. So computational imaging display is pretty much everywhere. It's in space, it's in medical imaging, but probably the most exciting area right now, especially being in the Bay Area here, is wearable computing, augmented reality, and virtual reality. And each of these companies working on things like this, they have teams that do the camera sensor array. They have teams that work on the computer vision and image processing. They have teams that work on the optics. And of course, they have teams that develop the experiences and design interfaces with that, right? So you can think about this as something that brings all of these disciplines together. Just to give you an overview of my group again, we work on computational photography, displays, and light transport. So we work a lot on optics, electronics. Here's a photo of my group. These research areas are really closely related to a lot of other things, including human-computer interaction, computer graphics, but on the other hand, also things like scientific computing. So for example, we collaborate with SLAC, the particle accelerator, quite a lot. They do a lot of scientific imaging and do a lot of image processing. So the students in my group work on 3 different areas. I want to just give you a sense of the kinds of stuff that we work on because, and I'll focus more on HCI-related things, but we actually work a lot on microscopy too, in particular fast, high-resolution 3D microscopy. In this video here, you can see a little worm. It's called C. elegans. It's a model organism that neuroscientists use all the time. It's very small, completely transparent, and it's genetically modified so that all the neurons emit light, fluoresces. Whenever there's an electrical signal going through these neurons, the fluorescence changes. So we can use computational optics to capture this 3-dimensional volume in real time, segment out these neurons and analyze them. For example, with techniques like light field microscopy, to get volumes out of that that we can then analyze and correlate. This is not so much related to HCI. I just want to give you a sense of like where computational imaging can have an impact. So we want to measure these time-changing neuronal activity patterns, correlate them, and correlate them with external stimuli too. Some of the computational photography techniques that we've been working on lately include things like time-of-flight cameras. Time-of-flight cameras are usually used as depth cameras. So for example, the Microsoft Kinect, everybody probably knows that, is actually a time-of-flight camera, at least the latest generation. That means there's a light source in there that sends temporally modulated illumination into the scene. It reflects back to the sensor, and there's some low-level processing and electronics going on the sensor to give you a sense of the depth. So what we did is we hacked a time-of-flight camera, or we built an experimental time-of-flight camera, where we have full control over all these illumination patterns and the sensor modulation too. And we built the first consumer time-of-flight camera that also measures velocity instantaneously. So these temporally modulated patterns actually change their frequency when you have moving objects. So when Isaac is riding his bike towards the camera, the temporal modulation pattern is slightly changed by the Doppler shift, ever so slightly. But by putting intelligent algorithms onto the camera, we can analyze that Doppler shift and instantaneously estimate a per pixel velocity map. So it's kind of like the radar speed gun, but integrated in every single pixel of this time-of-flight camera. And this was the first prototype we built. There's still a lot of artifacts. We've been spending a lot of effort on the hardware development. But you can think about playing Fruit Ninja by measuring velocity and depth to get yet another imaging modality that allows you to put interfaces and new kinds of experiences on top of that, right? So for example, here we had a little ping pong gun and we're shooting ping pong balls towards the camera. So you can see in the velocity map that you can measure how fast things are moving instantaneously, right? So that could open a lot of new possibilities for HCI as well.
I was just wondering, in what way would this sort of give you an advantage over sort of taking a delta on the depth graph and getting velocity from the...
Yeah, so when things move fast, the delta on the depth map oftentimes doesn't work. Also, there are very few features that it's much harder to track these depth maps between two consecutive frames than, for example, textured images, because there's not a lot of texture in the depth map, right? So instantaneous velocity could open up completely new possibilities. And that's something that we're making practical right now. But it's interesting to think about how we're going to use that later on, right? So the group has been focusing a lot on light field displays. As I said, normally you would think about television where you and your friends can sit around the television, get a sense of depth in that scene. Everybody gets to see multiple different images with their eyes. So you see one image with your right eye, you see a different image with your left eye. As you move around, you have to make sure your eyes are always in a different viewing zone. So in order for that to happen, the display has to emit all these different perspectives of the same 3D scene in slightly different directions. And that's what's usually called a light field. The light field is really just this collection of 2D images showing the same 3D scene from slightly different perspectives. And that's an idea that's been around for more than 100 years, actually. So Frederick Ives in 1903 invented what he called a parallax barrier. So he mounted an array of pinholes just in front of a 2D display so that when you move around, you see through the pinholes, but every time you only see a subset of the pixels of the screen, and that allows you to see different images from different perspectives. But it's very low resolution and very dark. So another popular approach, and this is what you see for most 3D televisions today, is called integral imaging. It's also 100 years old. They basically mount small microlenses onto the screen so that the light from different directions is focused, again, on different subsets of pixels on the screen. It's a little bit brighter, but still low resolution. So in 2012, we came up with an entirely new paradigm for designing these types of displays. We stacked multiple LCDs on top of each other. They actually see through if you just remove the backlight, if you remove all the electronics. If I rip out the LCD from my screen, hold it up, it's transparent. And each pixel is a programmable attenuator, right? So I can electronically change the amount of light that's being transmitted through it. So by stacking them up, we have a lot more degrees of freedom of controlling every single ray that's being emitted from this screen. And what our contribution really was is to develop the optimization framework, the algorithmic framework that actually computes the optimal set of patterns for a particular content, right? It's a content adaptive display, if you want. We also use time multiplexing. So here you can see the screen. But the LCDs are much faster than what we can resolve visually. So if we take a high-speed camera, we can see these patterns that actually change very rapidly over time and that are optically overlaid over these layers. And when they're all optically overlaid and temporally integrated in your retina, they create this illusion of a high-resolution 3D scene floating in space. And that was really exciting because for the first time, we could overcome a lot of these fundamental limitations of optics design only using this idea of computational optics. It turned out that a stereoscopic 3D was a big flop and people didn't really care about it, right? So the industry bet a lot of money on it in that time from 2008 to 2012, 13 or so, but people didn't really care about it so much. So what we focused on after this project was more to find the killer app of 3D displays. And yes?
So do you think people didn't care in that they didn't want to watch 3D or they didn't want to wear glasses or something at home?
I think a little bit of both. So people didn't want to wear glasses, and the movie theater is great, right? And that's where it really works well. But for stereoscopic televisions, they came out, everybody had one, but nobody ever really used it, right? Because I think what the mindset of the content creators was that we're just going to put the same movie on there that we had before, just filmed with 2 cameras, and people will like it twice as much. But that's not the case, right? So, but I think when you think about developing interfaces and making tasks more efficient, then it makes sense to think about 3D user interfaces. But for just watching stereoscopic movies on a television, it didn't really take off, at least in the industry. So we set out and said, okay, let's try to find the killer app of 3D displays or light field displays. And I think that interfaces is one of them. But another one, a cool idea that we had was this idea of a vision correcting display. Right? Many of us wear glasses, and what they do is they correct visual aberrations in our pupils. So what we said is, can we build a display that can correct for these visual aberrations in the screen already? And And we did this conceptual study, which we call a vision correcting display. The idea is that you also have a light field display, and you pre-compute the pattern, in this case, the little bunny there. What you can see is that the camera now with a realistic pupil setting is totally out of focus, right? It simulates somebody having myopia or hyperopia. Buttons are out of focus. You can't read the font. But when you pre-compute the special pattern and observe it through the parallax barrier, it appears to be in focus. So that was extremely cool. And we got a lot of response from a lot of people. It's an extremely challenging engineering problem to actually build this because you need very precise eye tracking. You need to know the pupil size, the location, the prescription of the person. So in a lab setting, it worked pretty well. But to get this into a tablet is actually, that's a major engineering effort. But the promise is really good. And we got so much positive feedback from people we had no idea were interested in this kind of technology. And at the end of the day, it's the same thing as a glasses-free 3D display. So in this case, you can see the comparison between vision correcting display and conventional display. Just give me 1 sec. What the engineering challenge, just so you get an idea of what it takes to build something like this, is this. For the 3D display, you want to see one image with one eye, different image with the other eye. And as you walk around, you always want to have different viewing zones. For something like this, what you need to do is you need to get multiple different perspectives of the scene into the same pupil. So I want to get an array of different images into different parts of the same pupil to enable this refocusing mechanism. And I'll talk more about this in a second for the head-mounted displays because we've been doing the same thing there. But just to give you an idea of how challenging this is optically and electronically. So you had a question.
Just wondering, in order to do this though, wouldn't you need multiple screens? So I mean, would that actually fit within the smartphone? The earlier thing that you showed us looked pretty deep in, right? I mean,
Yeah. So in this case, oh, I don't have the picture of this is an iPhone, and what we did is we took a plexiglass sheet and put a printed mask on top, this parallax barrier I showed you a little while ago, because it was the easiest to do. We just sent it to a printing shop, they printed it at a high resolution, we put it on a little spacer that's about this thick, put it on an iPhone screen, that's what you see here. Right, so you could integrate it into a phone. The form factor would change a little bit, right? But again, this was more of a conceptual study. Can we build a proof of principle display that could potentially correct for your visual aberrations? Not just defocus, but also higher order aberrations. So a lot of people, when they get LASIK surgery, the higher order aberrations actually get pronounced. And that's something we simulated and works really well. So lots of potential applications for this kind of technology. But so now I want to go back to these AR and VR consumer electronics kind of devices. So in the late 60s, this guy, Ivan Sutherland, built what he called the Sword of Damocles at MIT. It was the first electronic augmented reality display. It was already see-through because he had these beam splitters. He had 2 CRT monitors, 1-inch CRT monitors on the side. He had an ultrasound tracking system that you can see on the right for head positioning and mechanical tracking too, so because it was attached to the ceiling. And with that came the need for computer graphics and generating computer-generated content on there too. So in a way, you know, this distinction between devices, electronics, tracking, augmented reality, optics, computer graphics, it was all the same thing. A lot of the ideas came out of this one group at MIT, right? And then we went off and did other things. He also invented Sketchpad. I don't know if you know Sketchpad. Who of you knows Sketchpad? Most of you, right? So that was a seminal paper, first pen-based interface, right? And I won't give it enough credit if I describe it, so I'll let experts in HCI describe it. But all of this were the same ideas initially and then ventured out. So the one thing that he didn't figure out, and that's what people haven't figured out until today, is how to get focus cues into these head-mounted displays. So normally when we think about 3D, we think about seeing 2 different images with the eyes. But even with a single eye, there is a lot of rich information that our visual system uses to distinguish depth. And that is focus cues. You can see that here. This is a camera, of course. It's focused on the finger. But there is this depth of field effect. And depending on where we're looking at, there's an autofocus mechanism in our eye that will change the muscular state, which sends a signal to the brain. And also this depth of field effect, which is a visual cue on the retina. Those two together make up actually it creates the experience, the sensation of depth for objects that are very close to us. And no existing display can do this. So if we look at all the different depth cues, and there are many of them, I don't have enough time to go into detail, aerial perspective, relative object size are for objects that are far away. So here's object distance to the viewer versus importance. These motion parallax and stereopsis cues are important for things within a range of a couple meters in front of us. But when we have things that are very close to us, within arm's length, their accommodation and these focus cues are critical, right? And no display can create these today, which leads to visual discomfort and so on. So when you think about touching stuff in VR or interacting with stuff, that's when focus cues are most important, actually. And so people sometimes get sick. So let me just take a step back and make absolutely clear what these focus cues are. So we have two eyes. In the physical world, these eyes are focused at a particular distance, and they also verged at that distance. So the eyeballs rotate in their sockets to verge on that object. When the physical object moves, the vergence of our eye also changes, so the eyeballs rotate to always verge on that object, and they continue to focus on the object too. So these cues are all coupled together, right? And that's how we grow up, that's how our visual system evolves. All these cues are coupled. Now, in a head-mounted display, if we now have a virtual object, we show two different images, one to each eye. That creates the correct vergence cues. But when the object moves farther away, our eyes verge, but the focus is still on the physical screen. Right? We cannot ever focus anywhere else other than the physical screen or the virtual image of that screen. And so these two cues are now artificially decoupled, and our brain receives conflicting stimuli. And that's usually what makes people sick. So think about motion sickness in a car. There's a difference between what our vestibular system senses, the sense of gravity, right? When the car drives, it's bumpy, so we feel the bumpiness. But we read a book, and the book moves with us. So the visual stimulus is static, so we don't see the bumpiness. So this difference makes people sick. And that is the same thing here. If the brain receives conflicting stimuli that are normally coupled, then bad things happen. So diplopic vision, eye strain, visual discomfort and fatigue, headaches, and things like that. So here I just illustrated what happens in the real world. The eyes verge and focus at the same time for objects at different distances. And here's a scene with these matryoshkas. And if we just take the scan line here, there is a little bit of parallax over the pupil, right? So this change in viewpoint over the pupil size, that's exactly what creates these focus cues. And when you think about displays today, that's just not supported. The image is constant over the pupil. So what that means is our eyes will rotate and verge correctly, but the focus is always glued to the screen. So what we did last year is we developed a technology that's based on our multi-layer LCD display technology, and we called it the light field stereoscope. We basically used off-the-shelf LCD panels and driver boards, put them all together into a form factor that looked very similar to what you know from the Oculus Rift, for example, right? All that we added is a second LCD panel, a little bit of a spacer, about less than a centimeter thick, so the form factor is the same. And then these algorithms, and the algorithms is really where all the contribution comes in. So just to give you a sense again of what's actually necessary, we have this light field entering the pupil, and the light field in this case is represented as 7x7 views. Right? So we have all these different perspectives. They may all look the same to you, but there's a little bit of parallax in there, and that's what we need to reproduce. With our two-layer LCD display in front of the eye, we can emit light rays that are multiplied between these panels. So we just work out the image formation, and we want to make sure that this view gets projected into that part of the pupil, and so on. Right? And that would create this parallax over the pupil so that your eye can freely focus anywhere after. Yeah, so there's a lot of math going on. Everything is implemented in CUDA on the GPU. What comes out automatically at the end is this two-layer representation of the scene that we put directly onto the pixel states of the display, and you can focus freely in the scene. Right? So both on the front and the rear panel, but also in between. So it creates this volume in front of your eye where you can focus your eyes. And that's really exciting. We've used mostly OpenGL to create the content for this, but you could use Lightro Camera as well to do this. And everything's in, OpenGL in real time. So there's a lot of CS component in there too.
Just help me build the intuition here. You're saying the challenge was that there's a single plane that my eye is focusing on. And you've now created two.
Yes.
So why is 2 equal to infinity?
Yeah, so 2 is equal to infinity because of this image formation. It's not intuitive, right? You would think that, okay, now I have 2 planes and I can focus on one or the other. And that would be true if you had additive panels, that like LEDs that are floating in space or transparent OLEDs where the contribution of the light sources adds up in an additive fashion. So what we have here is that the interaction between the panels is nonlinear. It's a multiplicative interaction. So whatever light is emitted by the rear panel gets along the ray. You can see that here. So this is one light ray, right? Gets emitted here and then gets blocked here. So these two interact by multiplying the pixel states together. And it's a very subtle difference to an additive image formation, which would be the same. If you use 2 OLED panels, it would be additive. But with LCDs, it's not. And this nonlinearity, this multiplication, gives us sufficient degrees of freedom to create a distribution of light rays that approximates the light field much better than what you could do with 2 additive panels. And in practice, that just means you can have stuff in between too. It won't be quite as high resolution, but it'll be better. That's a very good question. And most people that we show it to, I mean, they don't see that. I mean, they see 2 panels and they like it, but I mean, there is this mathematical difference, actually. It makes it much harder to actually compute these images, too. Okay, so let me show you some results so you get a sense of what you would see.
I was just wondering, what kind of frequency would you be able to achieve with something like this? Because you have to do the calculations and the math in real time, and it looks like you'll have to do multiple image projections through the screen to actually construct one image on a person's eye.
Yeah, so this may not be obvious, but you're right. It comes at a cost, the computational cost, right? So instead of rendering 2 images, we are now rendering 50 images, 25 images per eye. So you can see that here. 1 light field for the left eye, 1 light field for the right eye. And then we have to run this nonlinear optimization, the factorization as well. All of this runs at about 5 to 10 milliseconds per frame. So it's actually very fast. So we spent some time, a couple of months, optimizing the CUDA code. It runs in real time. I mean, we have the demo in Packard. If ever you come by, you can probably see it. We showed it to about 1,000 people or so at SIGGRAPH also. And it's very preliminary, the kinds of scenes that we have. But what I'm saying is that computation gets faster much quicker, right? Hardware doesn't get faster that much better. The resolution of panels grows very slowly, right? But the compute power grows very rapidly. So that's what we wanted to tap in here, right? Use some of that compute power to overcome some of these challenges. So it runs in real time at the resolution that I'm showing you, which is still pretty low compared to the Oculus Rift. So here's a traditional head-mounted display on the left, and on the right is ours. You can see that everything's in focus. So the camera is now focused on that panel, right? On the right, you can already see a little bit of this depth of field effect. So the robot is in focus, but the spaceship is out of focus. So now we're going to take the camera and we're going to change the focus to simulate what you would see if you were accommodating your eye at different distances. And what you'll see is that on the left, now everything is out of focus. And on the right, now the spaceship is in focus. So that's kind of the effect that you'd see. It's very subtle, but it makes a huge difference in the experience. Right? And there's no eye tracking going on or anything changing in the display. We're just pulling the focus of the camera in this case. Same as here. On the left, you can see everything's in focus. It's a very high-frequency scene. On the right, we can see the bush in focus, but the background's out of focus. And then we change the focus of the camera. And here's an example where you see these virtual hands. That's where it's really important, right, when you touch things. I mean, we're not very artistic, so we just downloaded some free 3D models from the internet and put them on there. So on the left, everything's in focus again. On the right, you can see this refocusing effect. What we also tried was to do live action content by taking a light row camera and capturing stereo images with the light row camera. So now what you have is basically a light field for the left eye, light field for the right eye with the light row, and then we take that exact data and factor it into this pixel representation. So we can actually capture photographs as well, or videos, but the light row right now doesn't support video capture. So I skipped a few things, but maybe I can give you a sense of where we've been going from here, because now it becomes also more relevant to HCI. So all of this, I hope I gave you a sense in the beginning that I think HCI, computer graphics, AR, VR is all the same thing, just slightly different perspectives on the same, bigger field. So some of the things we learn from the experience of the light field displays that it's incredibly difficult to convince consumer electronics manufacturers to really change their entire design process of their displays. So one of the things we found is an easier way of potentially increasing the accommodation range by changing just the focal length of the lenses in the head mount. So you take an Oculus, you take out one lens and replace it by a lens with a different focal length so that both eyes are accommodated at slightly different distances. So you may think that creates a lot of discomfort. It actually turns out that's a pretty standard technique in ophthalmology called monovision. So basically you have eyeglasses in that case where one eye is focused close, one eye is focused far. So if you want to see far, your dominant eye would switch to that eye that's focused far, and your brain suppresses the blurry image. If you want to read something, you would use the other eye. So it's something that we found by accident that people had done that in ophthalmology already. And so one of the things we did in the last couple of months is actually evaluating how effective this could be for VR, for example, too. So we're always developing new optics, but then also doing the studies on how effective it is, setting up tasks and testing users is extremely important to evaluate the user experience or the change in user experience, right? So it's something that I don't have slides for, unfortunately. We just submitted this as a paper also. And that actually almost concludes the talk. I'm happy to have a conversation about different things that you may be interested in. But the message that I'd like to send is that this intersection of human-computer interaction, device design, optics, electronics, computational imaging as well, is all very closely related together and very synergistic. So if you guys are interested in hardware in general, I'm just across the street, and I'm always interested in starting collaborations and things like that. So, sorry, I guess I'm done a little bit early, but.
Thank you. So we have plenty of time for questions, thoughts, reactions.
Yeah, so maybe start with you.
Is there any hope that at some point in the near future we're going to get 3D displays that don't depend on the viewer approaching it from a certain angle? Because a lot of these products were like close to the face or strapped to your face.
Yeah, I think that could be pretty easily solved with just putting eye tracking in there. So some of these incarnations of the displays can actually dynamically adjust to where you are. If they only knew where you are, it would be pretty easy. And there are a couple of companies pursuing this. I think that's something that we'll see in the next couple of years. But I think what's much more interesting to think about is then, let's say we have these devices, and people develop that for computer games, watching movies, and so on. What's much more interesting is to think about how do you develop, for example, 3D UI interfaces or things where this 3Dness actually gives you something that you just couldn't do otherwise, right? I think that's the more interesting question. Let's say it's there, what are we going to do with it? Right? And that's not obvious, I think, at least not to me.
In the case of augmented reality, any thoughts on how you could subtract light out, like occlude light instead of just adding light to a scene?
Yeah, so that's also one of the challenges, right? If we outline the challenges of augmented reality, there's a long list. So one big problem is that if you have a bright object in the physical world, like the sun, and you want to show, let's just draw this on the whiteboard, right? So most augmented reality displays use a beam splitter here so that you can see your micro display here, shows you an image at some distance, but you can also see the real world here. And let's say there's a bunny in the scene, right? And the display shows you another bunny. So if this bunny is very bright and this one is not quite as bright because we can't make the display as bright, we want to be able to do this occlusion. It's an extremely challenging problem. It was actually my first project I worked on in a PhD. What you can do is you can optically overlay an LCD that can block parts of this light, just like what I showed you with these transparent LCDs. The big challenge with these LCDs is that as the pixels get smaller and smaller, you get a lot of diffraction artifacts. So if you take the LCD, it's transparent, but the real world will be blurred based on diffraction blur. And the higher resolution the panel, the worse that effect gets. And so there could be ways around this, but that would have to be special engineered LCD or LCOS panels that mitigate that diffraction effect. But conceptually it's possible, practically it's very hard.
So let's say you have a head-mounted display with eye tracking coupled in. Do we have techniques right now to determine the accommodation of the eye, or the depth focus of the eye through tracking?
Yeah, so that's something that's a very interesting question. I'm not aware of any tracker that gives you the accommodation state of the eye. What people in ophthalmology usually use is what they call an autorefractor. It's a device that also has a beam splitter and a camera. And I'm not entirely sure how exactly they measure it, but there are multiple different ways. But it's basically a big device. So yes, you can do it, but not with a little eye tracker, I don't think. One of the things that we tried recently is if you have liquid lenses where you can programmably change the focal length, if you know where the user is looking at on the screen, you could always dynamically adjust the focus based on what you're looking at. So if I'm looking at you, in the real world, I would always accommodate to you. Right? And then I look at something else, and I just change the accommodation state. So it sounds easy, and that's probably the way to go, but it's incredibly difficult to build reliable eye tracking into a head-mounted display, especially with custom optics in there. So it's something we worked a lot on last year, and we never quite got it to work, and that's where we went back to just running user studies on asking people to fixate on specific objects so that they don't wander around, and then moving them with respect to each other, and then testing how effective that mode could be compared to having fixed focus. So that's kind of some of the user studies we've been running recently. I should have brought some slides for that, but unfortunately I don't. So it's much preferred. So the outcome is much preferred over fixed focus, for example.
So what you're saying is if you knew very precisely where the eye was focusing, you could assign depth value to all the different parts of the image and then just focus the image.
It's the other way around. So your eye will always be accommodated on the screen. So if you were to measure the accommodation state, it would always be on the screen. But if you know where the user is looking at and you pull out the depth map, then you know where they're supposed to accommodate, because you just do a lookup in the depth map, and then you just adjust the focus state to where they're supposed to look at. And basically what you do by changing the focus state of the lens is you virtually place that image farther away or closer at exactly the distance where that object is that you're looking at. So I think that could be the solution to overcoming all of this. But then I talked to a couple of people who are experts in this, and they said focus tunable optics, these liquid lenses are much too power hungry. Like putting that into a wearable display is impractical. So at the end of the day, there are so many different trade-offs for all of this. That's why it's so challenging. But a lot of good ideas floating around.
That'll obviously be solved once my shirt in my pants become one gigantic battery. But so I'm trying to think about you. I want to give you a soapbox for a second, because earlier you gestured toward content creation being a major challenge with like 3D TVs as an example.
Oh, yeah.
And I'm trying to imagine, let's say that what I'm looking at here was a gigantic version of one of your displays.
Yeah.
And so now all of a sudden, light field display was happening to my eyes. I was sitting here in this audience. And I was thinking about the amount of effort you would have to go through to make even just your slides more compelling.
Yes.
With that ability than they are on a 2D plane. I'm curious, like, what do you think it would take to sort of uninhibit that side of the equation? It seems like the authorship question is huge.
I mean, that's an extremely good question that not only applies to light field display in the screen, but let's say we have VR for everyone, like who's going to create that content anyways, right? How do we create content? How do we enable people to create their own content and be creative with these kinds of technologies, right? To be honest, I don't know. There are a couple of different ways, right? We can take pictures of real objects and digitize them, but just placing a static object into a scene, I mean, does that create a compelling experience? Probably not, right? PowerPoint is pretty convoluted already. I mean, we could imagine a future version of PowerPoint where we can animate things in 3D and put buttons in 3D, and it would probably make it even worse than it already is. But it's tough. I don't know, right?
Yeah, it raises this interesting question of which side you need to bash down first. Obviously, you can't create the demand without the
I think everything has to rise at the same time, and that's what I see. Like when you look at the VR AR kind of ecosystem, the VR ecosystem is ready to launch next year. So you have people working on camera arrays there, right, to capture stereo panoramas or videos of that. There's Google Jump. I think Nokia has Ozo. Samsung has Project Beyond. Google has Project Jump. Everybody has like some type of a camera that can capture stereo panorama videos with an array of GoPros usually. There are the content providers like Valve, who are going to have a platform where you buy your VR games probably. And there's going to be others who do the streaming, probably Google too, right? Then you have other companies who do all the displays. And so I think this entire ecosystem is very well worked out already. It's not one company that is everything, but they're all going to rise at the same time. And then either they're all going to be successful together or everybody's going to fail big time. For AR, for example, we don't have that ecosystem yet. So I think Magic Leap, for example, is a company that's very forward-looking, and they're probably like 5 years out to actually building something that we can see, but it'll take a while for that to happen. But thinking about the entire ecosystem for any technology is absolutely critical. And yeah, that includes the content creation.
In your slides, you had this grid of all the different viewpoints. Do you, like the human eye has like these different acuity regions, like they can see more detail near the center?
Yeah.
Do you somehow exploit that fact too, and maybe you can?
So we haven't exploited that yet. I mean, people have been talking about gaze contingent, foveated displays, things like this, right, where you want to have high resolution wherever you're looking at and lower resolution everywhere else. And that's definitely very interesting, especially when you think about streaming, compression, coding of large-scale visual data. I mean, I would say Bernd Giroux group, they do a lot of work in that space, but we're mostly interested in the devices, user experiences. Yeah.
All right.
All right.
Then we can thank our speaker one more time.
Thanks.